In this section, what we're going to do is talk about different ways you can use integrals. Again, this is going to be more application style stuff, and it's also going to be some things where we investigate different ways that integrals can be used. Word problems are going to creep up here. So let's just dive in. One of the things that we can do with an integral is find the amount of work done. So if we know a force equation and we know the parameters for that force from where to where, we can integrate it and get the work done. So here we've got the force f of x equals the cosine pi x newtons along the x-axis from 0 to 1/2 meters. So basically what we're doing is we're moving cosine pi x, so cosine is going to look something like this. Here's your cosine curve. With the pi in there, it's going to give it a little bit different shape, and we're just going from x equals 0 to x equals 1/2 of a meter, so we're not moving too far. This graph may not be drawn to scale either. Regardless, the setup for this is really simple. It's just going to be the integral from 0 to 1/2 because that's the distance that we're moving, and the function that we're working with is cosine pi x. My kids can punch this into a calculator. If you're not one of my kids, then you may need to go ahead and show your work on this. And again, it's not too hard because of the cosine pi x part. You will have a small u substitution where u is equal to pi x. But for the most part, it's not too difficult at all. So here we go. And I get 0.318. 0.3183, and I believe it's going to be the amount of work done right there. Okay, so there you go. It's just that simple. We need an equation for force. We need a start and stopping point. Once you have all that, you can find the work done. All right, we've got a leaky bucket here that weighs 22 newtons and it's empty. It's lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 4 newton meters. The bucket starts with 70 newtons, approximately 7.1 liters of water, at least at a constant rate, and just finishes draining as the bucket reaches the top. Find the amount of work done. So the easiest part of all of this is dealing with the bucket. Okay, remember, work is the integral of the force equation. So we've got a solid here, solid constant. That bucket weighs 22 newtons. So we're going to integrate on the leaky bucket, from 0 to 20 meters above the ground. And we're going to just integrate that constant of 22 newtons. Okay, and when you do that, you can put this in your calculator, or you can do this one actually by hand as well. It's not going to be too difficult, but it's going to wind up being 20 times 22. And 20 times 22 is 440. On the previous example, I forgot to give you your units, so I added it late, but this is going to be Newton meters or joules. So there you go, 440 meters for just the bucket. Now the water is a little bit different. We've got to figure out a way to show the water going from 70 newtons to 0 newtons. Okay, so think about this. We need an equation to integrate for that. Well, we start up here at 70. We get out here to 20, and we've lost all the water. Okay, so what have we got? Well, we've got 70 newtons of water. Okay, and then the rate at which we decrease. Okay, so think of a line. All right, this is a straight line here. So how do I find that? I need the slope. So 70, and it's negative, and then my rise over my run. I go down 70, forward 20. And there's the equation for the amount of water that I have left. And we can clean this up a little bit by eliminating a 0. So the actual equation I'm working with is y equals 70 minus 7/2 x, or 3.5. And we're going to actually integrate that particular guy from 0 to 20. So for the water, just the water, we go from 0 to 20 of 70 minus 7 over 2x dx, and you can use your calculator or do it by hand. It's either way is not horribly challenging, but you should wind up with 700 joules. All right, so now we're working with the rope, and here's the deal. The rope weighs 0.4 newtons per meter, so I've got 20 meters of rope, so I'm going to do 20 times 0.4, and that's going to get me a total of 8. Okay, so what I'm going to do is I'm going to, again, create a quick little graph. I start at 8. I wind up out here at 20 with 0, so I've got this line right here, and when I figure out what that line is, that's going to be y equals 8 minus, because I have a negative slope, 8 over 20x. You can reduce that if you want, and you can be working with y equals 8 minus and then 2/5 x. So that's what you would be integrating. All right. Go up here. I got a little more room. So we're going to integrate from 0 to 20 the equation 8 minus 2/5 x. And when you do that and you punch it in on your calculator, you should get 80. So I'll just do that real quick. 0 to 20 of 8 minus 2/5 x. And that's going to be 80. So if I want to know the work done lifting all these things together, then I have to add each piece of the puzzle here. So I'm going to add 440, I'm going to add 700, and I'm going to add 80. And when I add all those, I get the work done lifting the bucket, water, and rope all together, all at the same time. So 440 plus 80 plus 700 is going to be 1,220 joules. Okay, we got a conical tank filled to within 2 feet of the top with olive oil weighing 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? So let's get an idea of what this tank looks like. By the way, the tank is 10 feet deep. So we've got this conical tank right here. And goes back to the origin. And we're going to say that this line that forms a boundary of our tank, okay, we're going to say that that line is y equals 2x, okay, and we're going to say that the top of our tank, the very, very tip top of the tank, this will have a depth of 10 feet. Okay, so what we have in it now is we've got some oil in this tank, and the oil is filled all the way up, not quite to the top, but very close. There's 2 feet of space left, so there's 8 feet of oil. Let's get the different color. 8 feet of oil in the tank. All right. So we need to know how much work does it take to pump the oil to the rim. So remember, work is equal to the integral of the force equation. Okay. So we've got some math to do on this guy because we've got to be able to determine what that force equation is. We don't really know right now. So here's one thing that we do know. We do know that we've got to pump the oil to the rim of the tank. And if our if our rim of the tank is 10 feet tall, then the distance from the top of the tank to where the oil is would be 10 minus y. Now that's going to be important because it's going to tell us how far we've got to move that oil. All right, in this case it happens to be 2, but there could be some changes in there because there's a lot of oil already in the tank which needs to be pumped to the top. So how far does that lowest point have to go, or any point have to go? It has to move 10 minus y units to get to the top of the tank. The other thing that we need to look at here then is some volumes, because in order to move the oil, we're going to move a lot of oil, and we need the volume of one piece of the tank. And if I have the volume of one piece of that tank, the work done is equal to the weight of that one piece. So volume is going to be a circle, so it's going to be pi times radius times the thickness, okay? Or in this case, times height. And for us, we're moving along the y-axis. So the h part is going to be represented by dy, okay, the change in y, that's your thickness part. So the r value then needs to maybe be written not in the form of y equals 2x, but maybe in the form of x equals 1/2 y. That way we've got a constant variable. So if I'm going to have dy for this, then x equals 1/2 y will be my radius. And then pi, of course, is going to be, forgot that squared. Pi, of course, then stays as part of the area of, or volume of a circle. So this equation then becomes volume equals pi times 1/2 y squared dy, or pi over 4 times y squared dy. That's the volume part, and it's important that we have that, okay? The next thing we need to do is figure out how much one slice of that weighs. And so what we would do is we would take the 57 pounds per foot cubed and multiply it with the volume. That'll give us the actual weight of the thing. If I know what my cubic weight is and I know how much I have, when I multiply those together, that gives me my whole thing. So then I'm going to take 57 times pi over 4 y squared dy. All right, and that'll get me, this should get me really close to, starting to get close to the force required to actually lift that oil up. Lastly, I need to figure out how far I'm lifting. Remember, when we did these previous problems, I had to know how far I was moving stuff. And so to actually get the amount of work done to complete my force equation, I've got to multiply this guy by the distance that it goes, okay, the distance the oil goes. And remember, that oil changes as it moves. So the distance is going to be 10 minus y units. And so everything's in terms of y. So my force equation, force of y is going to be 57 pi over 4 times y squared times 10 minus y times the dy, the change in y. And this will be what I integrate right here. And how far are we moving all of this? Well, we're moving it all to the rim of the tank. And so we're going to actually move so what we want to do is we actually, if the distance to the rim is 10 minus y, I just basically need to integrate from 0 to 8, because that's the depth at which we're currently sitting. So from 0 to 8, I'm going to integrate this guy right here, which is the volume and the weight of one slab, and then how far we're moving it, which is the 10 minus y units. So we could have 57 pi over 4 times y squared times 10 minus y dy. And again, the 0 to 8 is the depth that we're at, and the 10 minus y covers us to the rim. Okay, so we get the beginning to the end of the actual depth of the oil, and then the 10 minus y gets us from that to the rim of the conical tank. So integrate this bad boy, and again, he actually doesn't integrate too bad, whether you do it by hand or whether you do it by calculator. So what you end up with, though, is 30,561 foot-pounds of work. All right. So there you go. That's a tricky question. There's a lot going on in there, and it's maybe something where you have to slow down and watch twice or ask another question. But there you go. Section 3 stuff.